Alice, Bob, and Eve explain quantum Monte Carlo.
I'm trying to estimate the average outcome of these dice by taking many random samples instead of calculating all possible combinations.
What you're doing is actually similar to a powerful technique used in quantum physics and computing called quantum Monte Carlo.
Quantum Monte Carlo methods are fascinating. They help us understand complex quantum systems that would be impossible to solve exactly.
How do my dice rolls relate to quantum computing?
Classical Monte Carlo uses random sampling to solve difficult problems, like your dice rolls. Quantum Monte Carlo extends this to quantum systems, where the mathematics becomes incredibly complex.
Imagine these dice represent quantum particles. The possible arrangements they can take, all their positions and interactions, would be astronomical in number.
So you use random sampling instead of trying to calculate everything?
Exactly, but with a quantum twist. Instead of sampling actual quantum states, which would require a quantum computer, we sample possible configurations using classical computers and clever mathematics.
In quantum physics, particles don't have definite positions like this die showing a specific number. They're described by probability waves. Quantum Monte Carlo creates a statistical representation of these waves.
Quantum Monte Carlo can actually refer to two different concepts: a classical algorithm for simulating quantum systems, or a quantum algorithm capable of surpassing classical Monte Carlo methods and leveraging quantum hardware.
What kinds of problems can you solve with it?
It's excellent for finding ground states of many-body quantum systems, studying quantum phase transitions, calculating properties of quantum materials, and even helping design quantum computers themselves.
In chemistry, it helps predict molecular properties by approximating the quantum behavior of electrons. In materials science, it helps design new materials with specific quantum properties.
Do quantum Monte Carlo methods always work?
Unfortunately, no. They suffer from what's called the sign problem for certain systems, particularly those with fermions, like electrons, where the mathematics involves cancellations that make sampling inefficient.
It's like if some of your dice combinations gave negative probabilities that had to cancel out positive ones. It would make your sampling approach break down.
So my simple dice rolling experiment is conceptually related to how scientists simulate complex quantum systems without needing actual quantum computers.
Exactly. Both approaches use random sampling to make intractable problems tractable. The key difference is that your dice have definite values when observed, while quantum particles exist in superpositions until measured.
And just like how you get better estimates the more dice you roll, quantum Monte Carlo simulations become more accurate with more samples, though they require significantly more computational power than your tabletop experiment.